Hi, I'm Susie Byrom, a rising junior at the University of Illinois at Urbana-Champaign. This summer, I worked with Dr. Jamie Tayar at the University of Florida on open clusters of stars and how they can be used to identify uncertainties in stellar evolutionary models. So, open clusters. There's good news, there's bad news, and there's maybe a solution. So, the good news is all the stars in a given open cluster are the same age and initial metallicity, which makes open clusters a really good calibration benchmark for stellar models. Unfortunately, there's a pretty wide spread of age estimates for a given open cluster. If you look at M67, it's 3.5 to 5.5 gigayears, depending on which model you use. And if you're trying to estimate the age of a star for your galactic archaeology or for an exoplanet age estimate, that means you're going to have some pretty big uncertainties in there unless we have some additional information. So this summer, as a possible solution, I examined 4 stellar evolutionary models and obtained age estimates for stars in the open cluster M67 to identify trends that depend on which model is used and other variables. So the typical method of determining the age of an open cluster is using isochrone fitting, where you match an isochrone to the main sequence turnoff of an open cluster. This is also how a lot of models are calibrated. Unfortunately, if you calibrate a model based on the main sequence turnoff, that doesn't always mean that it's well calibrated for the giants or on the early main sequence. So, in order to examine other evolutionary phases, I looked at age estimates of individual stars of M67. Using Apogee Data Release 17, I took the data including the rotational velocity v sin I, the surface gravity, log g, effective temperature, the alpha abundance, and the metallicity of the star. For each individual star, I matched it using the Python package Kiyohoku to a model grid to determine the age, luminosity, and equivalent evolutionary phase, or EEP, of that star. I removed stars with problems caused by the Apogee data pipeline and stars that were unlikely members of the cluster M67. Then I plotted the individual stars on a Kiel diagram colored by age. So here's the results of each of the individual stars plotted on a Kiel diagram for the different models. You can't really tell that much. It looks like on the main sequence turnoff, where it kind of gets wider, on the inside of that, the stars tend to be older, and it's most noticeable for the YREC models. However, it's kind of hard to quantify that. And even looking at a table, you can see, so the average age is around 5 gigayears, which is on the older side compared to isochrone estimates, but still within the range. And then it's further divided into different phases for the star. The early age main sequence, which is kind of at the beginning of a star's lifespan, the intermediate age main sequence, the terminal age main sequence, and then the red giants. And you can see each of those has a different average age across all of the models, with the red giants having by far the youngest age estimates. This is not ideal, because this means the models are not calibrated well for the red giant branch. To get a better idea of how models' age estimates vary with phase, it would be good if we had a number associated with how far along the evolutionary track a star is, and we do have such a number. It's the model-generated EEP, equivalent evolutionary phase, that I mentioned earlier. With a more detailed breakdown, I was able to pick out the 2 best models. Here's the first one, DSEP, or Dartmouth Stellar Evolutionary Program. Since all the stars in M67 are the same age, this scatter plot would ideally form a straight line, preferably within the gray bar of isochrone age estimates. But this is not a straight line. There are very visible trends. For all models, you can see here, the main sequence stars have consistently high age estimates, and then once a star begins to turn off the main sequence and become a subgiant at around 475 or 480 EEP, the ages follow a linear downward trend as a function of EEP. Dartmouth is actually the model that was the least affected by these trends. Garstek, on the other hand, has some issues in the center where you can see between EEPs of like 400 and 440. There's a pretty big gap there, so it's probably not the best idea to use this model for main sequence stars. But its red giant age estimates are actually quite reasonable, and it doesn't follow the same continued linear downward trend that the other models do. The main takeaway from this project is that model-generated star ages have high uncertainties, but some of that can be reduced by picking the correct model for the type of star you are working with. In general, using Dartmouth or Garstick is a good idea, although for subgiants on the terminal age main sequence section of a Keel diagram, there really aren't any models that are outstandingly good for the job. Continued research is needed to see if these trends are similar for different age ranges. This process could be repeated for other open clusters of different ages. Thanks for watching this presentation. I had a fantastic time this summer, and I'd like to thank my mentor, Dr. Tejar, for guiding me, as well as the University of Florida for offering this opportunity, and the National Science Foundation for funding my research.